All right, the next topic we're going to get into now is the anabolic pathways. Anabolic, if you remember, is all about building things back up. Catabolic is all about tearing things down and getting energy out of them. So again, you want to always organize your thinking, and here's how you do it. Anabolic pathways are going to go on primarily in the cytoplasm. Catabolic pathways are going to go on primarily in the mitochondria. And you remember catabolism goes on the mitochondria because that's where you're going to be making your ATP from in the electron transport system with oxidative phosphorylation. So anabolic is going to go on primarily in the cytoplasm. Here are a few exceptions. Glycolysis is the only purely catabolic pathway that goes on completely in the cytoplasm. And you can see that it was necessary for your body to do that simply because it allows it to be in a central location to feed into so many other pathways. And then we got several pathways that go on in both compartments. So pathways like heme synthesis, fatty acid synthesis, gluconeogenesis, urea cycle, and nucleotide synthesis, those 5 pathways are going to involve both compartments. Some of it going on in the cytoplasm, some of it going on in the mitochondria. But right now we're going to focus on anabolic, putting things back together. First, you got to remember, your body breaks down energy in the same sequence all the time. The sequence that we reviewed before was plasma glucose is the first thing your body uses for energy, and that lasts about 2 to 4 hours. Then liver glycogen will then be used for energy, and then it lasts about 24 to 28 hours, which means by approximately 36 hours, you really have no more glucose left in your body. So that's why your body starts to break down proteins and shunt those into gluconeogenesis. So if you remember back in amino acids, we talked about amino acids, which are glucogenic. So that's what your body's doing, breaking down proteins, claiming the amino acids, and then turning them into glucose. So after proteolysis, then it's lipolysis, so breakdown of fatty acids, and then finally ketogenesis, breakdown of ketones. So since your body breaks it down in exactly that sequence all the time, your body's going to put it all back together in exactly the same sequence. So this way, if you have an order in which you're thinking through the information, you're more likely to retain it. So first, as soon as you eat, you replenish your plasma glucose. Once again, as soon as you eat, glucose returns to the blood from the GI tract. This is how your body knows, especially the liver. This is how the liver knows that you've just eaten, which means the plasma glucose is now replenished. Think about it, a little while ago, the liver was sending glucose to other tissues, but now all of a sudden, glucose is coming back to him through the portal vein, meaning glucose just entered through the GI tract. So as soon as you eat, you replenish your plasma glucose right away. Now, as we go, we're going to bring in the pharmacology that plays a role in the management of these sugar problems. So we can sort of impair how fast you can absorb your glucose from the GI tract. And the drugs that we use for that are 2. The 2 drugs of which I speak are ascarbose and miglatol. Both of these drugs have the same action. Remember, I've always said, make sure you know the drug action. That's the #1 thing they're asking on any exam. So both of these drugs block alpha-1 glucosidase, an enzyme on your brush border of your GI tract. Without it, it makes it hard for you to break down some of your sugars. So it's going to impair the absorption of some of your sugar. So both of these drugs are used in diabetes, especially ascarbose, especially for what we term postprandial hyperglycemia, which means blood sugar that rises real high after a person has eaten a meal. You can bring it down some if you can inhibit how much glucose they can absorb. So that's how these 2 drugs work. So the first step, once you eat, your plasma glucose is now replenished. Remember, the plasma glucose now, after a large study called the DCCT trials, showed that the plasma glucose should start to stay under 126 for excellent diabetic control. Now the next step, after glucose returns to your liver, what's it going to do? Turn off gluconeogenesis. Once again, after glucose returns to your liver, you turn off gluconeogenesis. Remember the steps of breakdown is plasma glucose first, liver glycogen second. So right now we did the first step, plasma glucose is replenished. Second step is now you got to turn off gluconeogenesis. So liver glycogen has been used up during the starvation state. So now we need to replenish it. So the first thing you want to do is turn off gluconeogenesis. That means you're not going to be breaking down any more proteins or glycogen to make glucose. If you remember the enzyme that controls gluconeogenesis, pyruvate carboxylase, okay? So that means we can also manipulate this. There are drugs which can inhibit gluconeogenesis in the liver, used very commonly in diabetes these days, and that drug is called Metformin. And he has a brother called Pharmacology. So these two drugs can block gluconeogenesis directly in the liver. So Metformin now is a very popular diabetic drug. Why? Because it has been shown in a study to decrease the progression of pre-diabetes to full-blown diabetes by 35%. That's humongous by a drug. Diet and exercise decreased progression by 58%. That's huge. That's why there's such a big push now to get people to stick to the right diets and to exercise on a regular basis, at least 20 to 30 minutes every day. But bariatric surgery decreased progression by 91%. This is why you also see a lot more bariatric surgery being done in the general population. So drugs that can block gluconeogenesis, metformin. So we know how they work. What side effects can we run into? So you can use metformin early on when you diagnose someone with diabetes. That's probably the first line drug that most doctors would now use. One bad side effect is lactic acidosis. So it was seen more with metformin in the past, which is why metformin is most commonly used. But metabolic acidosis can really hurt a patient, especially when the lactic acid level goes above 10. If you remember, acidosis will induce the production of GABA, and GABA will eventually shut down the brain. So metabolic acidosis. Since metabolic acidosis has to do with the kidney, that's the reason why most doctors would check a BU and a creatinine to check renal function before you start this drug. Because if they have renal impairment already, then you have to be very careful about using this medication. Metformin also has another problem. If you mix with IV contrast, it has a habit of damaging the diabetic's liver. So if a patient is on metformin early on in a vignette that you are reading, keep that in mind that if they're going to have to do an IV contrast study, you want to stop the metformin right away. So that means for the best results, they say stop the metformin, wait at least 24 to 48 hours, and then do the IV contrast study. That's only when it's an elective procedure. But what if I got a patient who just had a heart attack or is having a stroke and I need to find out right away? So I need to do a contrast study of his heart. Then you need to stop the metformin right away. Number two, you need to give him plenty of fluids, flushing through the kidney. And number three, we give him another drug called N-acetylcysteine, which will help protect the kidney. You might recognize this drug because this is the same drug we use in treating acetaminophen toxicity. But metformin mixed with IV contrast can be very damaging to the kidney. So first side effect, metabolic acidosis. Second side effect was interference with interacting with IV contrast. So when you put something in metformin or pharmacology, then you have to watch out for those two problems. All right? Now, here's what typically happens. After you've eaten and glucose hits your duodenum, your GI tract produces some chemicals called incretins. The incretins, one called GLP-1, glucagon-like peptide, the incretins go to the pancreas to send a message. The message they send to the pancreas is that you've just eaten some glucose. So the first thing the pancreas does is turns off glucagon. So incretins' job is to turn off glucagon. And second, to enhance insulin production. Now, which makes sense because if your plasma glucose is going up, you need to push that glucose into the cells. And that's what incretins does for you. The problem is this: if you're a diabetic, the signal from the incretins is very weak, and in some diabetics, non-existent at all. So that means in a diabetic, without that signal, after they eat glucose, gluconeogenesis continues because glucogen release continues from their pancreas, which is why postprandial hyperglycemia is very common in some diabetics. So incretins are then broken down by a group of enzymes called dipeptopeptidases. So that means if you want to help a diabetic out, then what you want to do is increase this signal, the incretin signal, or block this enzyme from breaking down that incretins. So if you want to increase the incretin signal, then we have drugs like exenatide, and luglaritide. These two drugs increase the incretin signal. That means they send a stronger signal to the pancreas to tell the pancreas stop glucagon release and enhance insulin release. The good thing about these drugs is that they end up causing significant weight loss, according to the studies, which is why a lot more physicians are using them. Well, then there's drugs that can block the enzyme from breaking down incretin signals, and that would be just as helpful. All right, the drugs that block the dipeptopeptidase enzyme are called sitagliptin, vitagliptin, and saxagliptin. So we have 3 drugs that block the enzyme, 2 drugs that mimic the incretins. These drugs are now being used very actively in the treatment of diabetes. The incretin mimetic drugs are more favorable because they cause weight loss, whereas the DPPI inhibitors are weight neutral. So there was no weight loss and there was no weight gain. Okay? So what have we done so far? We've replenished plasma glucose, and now we've turned off gluconeogenesis in the liver. After you turn off gluconeogenesis, the third thing you now must do is turn on glycogen synthesis. So you've turned off gluconeogenesis, that means the liver is no longer sending out glucose to the plasma. Now you need to turn on glycogen synthesis. That means the glucose that's returning back to the liver can now be stored as a larger molecule called glycogen. So glycogen synthesis. Now the hormone is going to control all of these anabolic processes is insulin itself. Remember, insulin is called a growth factor because it's going to push your body to store up all these nutrients and therefore cause the body to grow. Cells will enlarge. So fatty acid synthesis, amino acid synthesis, protein synthesis. So glycogen synthesis is also controlled by insulin. That means the second messenger for all this would be tyrosine kinase, the second messenger for insulin. Secondary second messenger will be cyclic GMP, since cyclic GMP is the parasympathetic system. And rest and digest goes with the parasympathetic system. So glycogen synthesis is the next pathway that we're going to look at. So let's go through that. The protein you're going to need to make glycogen is a protein called glycogen. Glycogen has a hydroxyl group sticking out at carbon number 1. The way to remember that is you're always going to make an alpha 1,4 bond. So it's always carbon number 1 attacking carbon number 4 of the next glucose residue. So glycogen is the protein you need to make glycogen. Notice the name is similar to what process you're about to undertake. So glycogen is a bunch of carbons, and if you remember, carbon-carbon bonds have no entropy in it whatsoever. So that means by themselves, they have no desire to be involved in reactions. So what does your body have to do? You have to make this bond high energy. So the way it does that is use UTP. You'll put a phosphate group on this oxygen, so now you have glycogen O phosphate plus UDP. This way, what you've done is activate this compound. activate this carbon specifically, which means glycogen now has an oxygen with a phosphate next to it. That makes it a high energy bond if we can get rid of one of these structures. So how are we going to do that? You take the glycogen-phosphate, so let's bring that back over here. And what you're going to do now is bring a carrier over. So let me introduce you to the number one carrier for any time you want to add a sugar to any structure in biochemistry. So once again, I want to make sure you heard me. The carrier for adding one sugar to any structure in biochemistry is called UDP. And UDP always runs around with a sugar attached to it. Most of the time it's glucose. So you see UDP glucose. So that means if ever you're asked who's the glucose donor or who's the sugar donor for any structure that's seen in biochemistry, always say UDP. And just to be complete, if they ask you who adds multiple sugars to any structure, that guy is called dolicho. So at this point, we got UDP with a glucose attached to it. So what are we going to do? UDP is going to grab this phosphate from our initial structure. By grabbing that phosphate off of here, that makes it favorable because you removed PO4 away from this oxygen. That means there's entropy in that reaction. So now, by doing that, you create energy so that this glucose can be attached to this oxygen. When you do that, what do you have? You now have glycogen. So glycogenin, O, glucose, who now has an OH group sticking out to the right. So you see, after you've added one residue to it, you always have a carbon number 1 sticking out to the right. And then look what happens. You get your UTP back from this structure right here. So that's why a lot of newer biochemists are arguing that the name of this enzyme should be called glycogen synthase. Synthase, if you remember, means it does not use ATP. Well, the older biochemists say it should be called synthetase because you do use ATP in the form of UTP, but you get the UTP back. So there's no net utilization of energy. So either way is fine, but just so you know why some books say glycogen synthase and some books say glycogen synthetase. So after round number 1, I got my glycogen with a glucose attached to it. Now, from now on, all you do is just repeat the same cycle over and over again. You have to phosphorylate this carbon again. Then you have to bring UDP with another glucose residue and do the same thing again. So the way I'm going to illustrate this going forward is simply this way. Here's the glucose residues. So glycogen synthetase can add 8 to 10 residues in a straight chain. And all of these residues, 3, 4, 5, 6, 7, 8, 9, 10. All of these residues in a straight chain would be an alpha-1,4 bonds. So that way you're never guessing. Every residue that's in a straight chain is an alpha-1,4 bond. All right, so that's glycogen synthetase. Then, after the 10 residues, you now come to branching. So we properly name him the branching enzyme. The branching enzyme. So what if your branching enzyme was not present? Then that means all you have is straight chains everywhere. Okay? So glycogen synthetase does this. And then branching enzyme puts this residue on. I'm just going to make it a square so that you see there's a branch point. The branch point is always alpha-1,6. So if they wanted to name glycogen synthetase a long way, they'll just call it a glycogen, and then what are you doing? Transferring a glucose residue at alpha-1,4 linkage. So to be called glycogen alpha-1,4 glucosyl transferase. What about the branching enzyme? What you're doing is moving an alpha-1,4 linkage to an alpha-1,6 linkage. So the branching enzyme, you see alpha-1,4 to alpha-1,6 glucosyl transferase. All right. Once again, if you don't have a branching enzyme, you won't see these branches. That means all you're going to see is linear glycogen everywhere. And that's called Anderson's disease. So Anderson's disease will give you less glycogen than normal because you're not able to branch. So we'll go through the signs and symptoms shortly. But Anderson's disease, the way you know it easily is because all you see is linear glycogen when you do a liver biopsy. So it's very easy to diagnose with a simple liver biopsy. All you see is linear glycogen, no branch points whatsoever. Okay? So now after we make a branch point, then glycogen synthetase will take over again. 4, 5, 6, 7, 8, 9, 10. Every time you branch, notice there's an OH group still sticking out. Then you make another branch point with the branching enzyme. And then he does the same thing. 3, 4, 5, 6, 7, 8, 9, 10. Every time you branch, notice there's always an OH group sticking out. Why do you want to do that? When you have OH group sticking out, it adds to the water solubility of glycogen, which is why glycogen is easy to mobilize and to be used for energy, because you have OH groups. As it turns out, 1 gram of glycogen drags 3 grams of water around with it. This is why that organ that contains the glycogen weighs so much, because water is so heavy. So the question then becomes, where are the major organs that produce most of your glycogen? Number 1, 90% of your glycogen is actually produced and stored in skeletal muscle. This is one of the reasons why skeletal muscle weighs so much and skeletal muscle drags around so much water. Not only do you have the phosphates or the protein dragging water, but you also have the sugars, the glycogen within the muscle that drags a lot of water. Okay? So skeletal muscle produces the majority of it. Second is the liver. This is why your liver is so big. When you look at the liver, 3/4 of that liver is primarily water, and that water is held onto by all the glycogen stored within the liver. Third place is your intestinal wall. So the intestinal wall can suck up a lot of water, especially if the intestines are not moving. So this is why if you have an ileus meaning the GI has stopped moving, it is so easy to get third spacing. Third spacing means there's a lot of water in the walls of the GI tract. So a patient who has pancreatitis, let's say, can come in and without any vomiting be still severely dehydrated. And they may ask you, where's all that water gone? It's in the intestinal wall. So that's the third location. Fourth location is going to be the adrenal cortex. The adrenal cortex is a small amount. What for? It means that anytime you're stressed and you get an adrenaline rush, as epinephrine is leaving the adrenal medulla, it goes to the cortex and causes release of glucose from the glycogen until it makes its way around to the liver to cause massive release of glucose from glycogen. So it makes sense why that's there. And then number 5 is the cardiac. The heart is able to make some glycogen, and the heart uses its glycogen for itself, just like the intestinal wall and skeletal muscle. Only 2 of the organs can actually mobilize the glycogen to your glucose, and that is your liver and adrenal cortex. Okay? So when you were breaking down glycogen, remember glycogen breakdown under the catabolic processes, you needed more enzymes in this. To make glycogen, you only need 2 enzymes, glycogen synthetase and branching enzyme. If you were trying to break down glycogen, remember you started out with phosphorylase to phosphorylate these glucose residues. Then you needed a deep branching enzyme to remove this one branch, or the 3 that are outside of the branch. And then you needed an alpha-1,6 glucosidase to remove the one branch point. And then at the end, you still needed a glucose-6-phosphatase to finally mobilize the glucose into the plasma. So glycogen synthesis is a much simpler pathway with only 2 enzymes working, glycogen synthetase and then branching enzyme. And once again, if you're missing the branching enzyme, it's easy to diagnose. We call it Anderson's disease, and you'll notice only linear glycogen when you do a liver biopsy. So glycogen synthesis is now complete and stored away. So we've done our plasma glucose, we've turned off gluconeogenesis, and now we've replenished our glycogen.